The chapter 8, of course, you know, was all about air masses. And this chapter is about where air masses meet and how air masses make big weather systems. Okay. So that looks like, you know, you've been to spotter training. It kind of looks like you're looking for almost looks like a wall cloud. So you're looking for the funnel somewhere there, right? Okay. So if you're like me, it's the severe weather that kind of gets our interest peaked and gets our adrenaline going, you know. Severe weather comes in different forms, but severe weather often occurs at the boundary of two air masses. And an air mass, like we said, is it still snowing? It was snowing earlier, wasn't it? Air masses are distinguished by how much moisture they have or don't have and their temperature. Okay, so where they meet, we call that a weather front. So there's kind of an assortment of fronts. I have 4 fronts listed down here, and there are a couple of other miscellaneous fronts. But you're probably most familiar with a cold front. Okay, a cold front means that we have cold air is being the aggressor. That's why we call it a cold front. Now, one of the things you're going to want to kind of familiarize yourself with is in a cold front, it's blue with triangles. Okay, and the triangles are pointed the direction that the cold air is moving. Okay, so right next to it is a warm front, and a warm front is red with semicircles. In this case, I see the semicircles are kind of over here on the right, so actually that would be warm air pushing this way. Okay, so the semicircles show the direction of the warm air. And then we have a stationary front, and a stationary front is like a standoff. I think we might have talked about these before, where basically I can see by the direction of the red semicircles that we have warm air over here, and we have cold air over here, and it's not moving, it's stationary. So I posted on my other course's Twitter feed the other day just some strange kind of stationary fronts. I know he's kind of, he'll just keep going and going as long as there's water there. His head's getting cold. And then we have occluded front. And occluded front actually is not just a pair of air masses, but actually it's a third air mass. So there's 3 air masses involved in an occluded front, and we'll talk about what those are. But they're usually purple. Notice they have semicircle and triangle on the same side, so actually we can get a sense for direction with an occluded front too. Okay, so and this slide just kind of breaks them out, each one. So the 4 main types of weather fronts that distinguish the boundary between 2 air masses. So one of the things this chapter talks about is this big, well, it's a medium size, so it's a mesoscale weather pattern called mid-latitude cyclone. Mid-latitude cyclone is great because it actually ultimately has all 4 types of weather fronts. Mid-latitude cyclones, like the slide says, sometimes can, or I should say here in North America, kind of oftentimes take over our weather, our interesting weather anyway. So mid-latitude cyclone, and actually sometimes a mid-latitude cyclone is just called a low. Mid-latitude cyclone is characterized by a central low pressure, which we've talked about. That's a cyclone, right? And of course, these white things here are isobars, so we are stepping down, we're stepping up with regard to pressure. And then I kind of liken it to a mustache. We kind of have the cold front here and the warm front here. So of course, the cold front is with this counterclockwise movement associated with a cyclone. The cold air is coming down, the warm air is going up. It's kind of like a mixer. Okay, mid-latitude cyclone, you know, a low. So we'll be talking more about mid-latitude cyclones. So here's another weather map of a mid-latitude cyclone with just a little bit more on it. Notice you kind of see this, what I mentioned before, the characteristic cold front, the characteristic warm front kind of swung around counterclockwise by the low. But now you see that purple thing, that occluded front, that thing that we need to talk more about, that occluded front kind of up here. That's actually joining the cold front and the warm front. So this is a mid-latitude cyclone in one of its mature stages. One of the things, many things I like about this textbook is it has these segments, like this says segment A to segment B. So what you do is you find A and you find B. I just think that is so cool. So this little inset down here actually goes right up there, right here. So what they're doing is they're showing you, and we talked about this in chapter 8. Okay, 8, you guys should hopefully know what does CP stand for?
Continental polar. Yep.
Continental polar, yep, very good. What does MP stand for?
Maritime polar.
Maritime polar, perfect. MT?
Tropical. Maritime tropical.
Maritime tropical, exactly. You guys got it. So we kind of, with these mid-latitude cyclones, kind of have that L kind of being a mixer, bringing down the dry, cold air, mixing it with the warm, moist air, and then we have the cold, moist air over there. Yeah. And we're going to talk more about weather fronts, but this is very characteristic, and I think I probably mentioned this before. So this segment right here is right here. So you can see what the cold front does. It's very abrupt. Oftentimes that is where we're going to have our thunderstorms. This looks like a thunderstorm cloud. Okay. The warm front, on the other hand, is right over here. Okay, associated with this right here. It's going to, your warm air is less dense, and you can get your first look again at what it does. It's less dense, so it goes up and over the cold air in front of it. Okay, and that kind of gentle or gradual transition zone, it doesn't lend itself for the instability that the abrupt transition zone does of a cold front. Okay, so, oops, sorry. One more thing to put up there. So, yeah, warm air rises in your house. Cold air is more dense than warm air. Okay, and so that's kind of what we've got going on here. Oh, I like what I grabbed from your textbook, that the mid-latitude cyclone has several names. Like I said, sometimes it's just called a low. Sometimes it's called an extratropical cyclone. If you remember this in, I think it must be chapter 10, when we come back after your unit exam, we're going to see how actually a tropical cyclone or a hurricane can kind of move, recurve around those semi-permanent highs in the ocean basins and become extratropical cyclones. Okay. So let's look at kind of the fronts individually. So a warm front, remember it's a red line with semicircles. Warm front, like I said, the slope is more gentle. You kind of see it going up and over. One of the things, and actually I don't know if this is a homework question or a test question, it must be a test question, but we get this, and the word for it is overrunning. There it is. We get this overrunning because the warm air is less dense, so it kind of goes up and over. It kind of reminds me of like a mosh pit or something. You just go. Okay. And what I started to say about on your test is we get this kind of series of high flat clouds. So if you are over here, okay, waiting for this warm front to come, look at the first cloud that you're going to see. You're going to see those cirrus clouds. And I know a lot of times students have come and they said, my dad says that if there's a ring around the moon, then that could be that we're going to have some sort of precipitation coming. That ring around the moon, you know, is probably a halo or a corona that's caused by those wispy, thin clouds. And so actually those those high stratus clouds could be precursors to lower and lower stratus clouds and ultimately rain clouds. So that is true. Overrunning. Oh, I guess it was there.
Half that sentence is
blocked
Yeah.
off. It's like behind the picture or something.
Half of that,
Or it's just
oh,
this look like hand something.
Yeah.
gotcha. Yeah, is that better?
Yeah.
Good, thanks. Very good. So whether it's a cold air mass doing the pushing of the warm air in front of it, or the warm air overrunning, going up and over the cold air in front of it, that's a type of frontal lifting that we talked about. And if you get a chunk of air rising, it expands and cools. You can cool to the dew point temperature. These clouds. All right. So this one actually is a little bit different. It's another warm front, but it's a warm front in what we call not stable, but conditionally unstable. Remember we talked about that before? Conditionally unstable air. So what this air that's overrunning this dense cold air has brought is basically some moisture with it, and the latent heat of condensation has basically made it unstable. And so notice that we don't have our we have a chance here, instead of have nimbostratus precipitation, we can get precipitation from cumulonimbus clouds. I used to, for the longest time, kind of de-emphasize this idea that you could have a warm front, conditionally unstable, bring you severe weather, but you can. Notice, like this slide says, one of the things warm fronts can do is with this overrunning is you can actually end up with a pocket of cold air under warm air, which actually is a temperature inversion. So you can actually have the precipitation melt and then refreeze, which of course is our sleet or freezing rain. So that's all bad. I think your textbook does a good job for each of the, I know the warm front and the cold front, what he's done, or they've done, is basically say, what would you expect with regard to, what would you expect before the front comes, in this case a warm front, as the front passes, and after the front passes. So with regard to temperature, not so surprising, it should be warmer after your front's passed. Let's look at pressure. What did we say about pressure? If it's falling, we said you can expect precipitation, yeah, or changes in the weather. And then after the front passes, we should expect it to rise. So that's pretty good. I've put together, when we talk about weather forecasting, there's an old book, like the 1970s, used to be in our library, talked about proverbs, how to anticipate or predict what the weather's going to be. And there's all sorts of proverbs, like, have you ever heard, like, if the crickets are cricking, that can be an indication of precipitation or not, what the frogs are doing. Another one is if your doors are swelling or if they're not swelling, if spiders are doing their webs. A lot of those things have to do with animals actually responding to high humidity. So, yeah. That's kind of interesting. So that was all a warm front. So you can actually get severe weather with a warm front. A cold front now is where you will get your severe weather if the air that's being lifted in front of the cold air mass has some moisture to it. So the transition zone is relatively abrupt, and it's that abrupt transition zone. And the other thing about cold air masses that are associated with these cold fronts is they move very quickly. And so not only is your transition zone very abrupt, but it's moving very quickly. So it kind of brings chaos with it. Like this says, your precipitation events should be if it's severe weather associated with a front, which we have severe associated with other weather associated with other things, but it should be relatively short and intense. Okay, so here is a similar table. I was just curious, I hadn't looked at it very closely. Pressure, let's see. Yeah, it says if a cold front is coming, that the barometric pressure will fall, and then it will rise. This says it'll rise as it passes and after it's passed. In both cases, as the front has gone by, you know, you should have drier air. All right. So this was new to this edition of your textbook. I brought in something called the Backdoor cold front. And in order to make sense of it, let me grab the globe here. So one of the things we did in Chapter 7 was we spent some time talking about, well, we spent some time talking about a lot of things, but we talked about ocean currents. So let me find North America. Okay, so we said that we have a semi-permanent high here, a semi-permanent high here, kind of associated with the Hadley and the Ferrell cells. So movement in the northern hemisphere around a high is clockwise. So here we go like this, okay, here we go like this. So this sort of phenomenon, honestly, is kind of related to this sort of air pattern, I said oceans, but air pattern, kind of swinging, I wasn't going clockwise. Yes, it was. Okay, swinging cold air down. Okay, just kind of like you see there, swinging it down. Which is weird because you think Ferrell cell, and you're like, dude, that's like in the Ferrell cell. So where's my mid-latitude westerly? Well, the rules were made to be broken. So that's kind of, we have a prevailing westerly wind, but we definitely have some easterly sometimes sneaking in there. Okay, so a stationary front, like I said, is you have two air masses, a cold and a warm, and the word stationary kind of gives it away. They're not budging. Neither one are really moving. So like the slide says, this slide says that a stationary front is tricky to draw in, but I would say all weather fronts must be tricky to draw in. Because if you look at some of your favorite internet sites for what are they saying the weather's like, you'll get different weather maps. They'll be like all over the place sometimes. You're like, really? Is this even the same data? Okay, so that's stationary, a stationary weather front. So now I want to try to explain that third front called an occluded front. And I told you it had 3 air masses, and it does. Has 3 air masses. Remember, an occluded front is indicated by usually a purple line. I was trying to think. Oh, yeah. But how could you tell, if you were colorblind, how could you tell that occluded front from a stationary front? Stationary fronts have alternating. It's darker. I believe that. Is there something else or something else?
Looks like the circles and triangles, or the half circles and triangles are facing the same way.
Mm-hmm. Yep, they're facing the same way for the occluded front. Yep. So if you're colorblind and you see them alternating on either side, then it must be a stationary front. Yep. But if they're on the same side, it must be an occluded front. So at the crux of this is to keep in mind that cold air travels more quickly. Okay. So with that in mind, it kind of looks like, let's see what my slides look like. Actually, there are two types of occluded fronts that I want to run past you. But cold air travels more quickly. So actually, I think I have 3 kind of insets like this. So this is the first of 3 insets. Okay. But if we picture this cold air moving more quickly than the warm air in front of it, and honestly, it's going to catch up with the cool, not cold, but the cool air basically in the sector in front of the warm air. So what happens is this warm air is lifted up. That's how that works. It's, you know, we talked about overrunning. It's kind of like, a little bit like overrunning, kind of. So you have 3 air masses. And this is a cold type occluded front. So it's just kind of your author showing you, again, with the kind of the little dotted segment here, segment here. Okay. So occluded fronts can, like you see the figure showing you, can definitely bring severe weather. So we're going to talk more about the weather system called the mid-latitude cyclone. Just an L, begins with a mustache, then we get the occluded front, okay, kind of in the cold and the warm front. And the phases are just kind of what you see here. One of the phases is actually you have a little bit of occlusion, and this is actually called elongation, where the occluded front gets longer. Actually, during this last one, when the occluded front gets longer, it's kind of the beginning of the end for the mid-latitude cyclone. So that was the cold type, and don't worry, on a test, I'm not going to ask you the difference between a cold type and a warm type, because I don't know if I could distinguish them necessarily. But this is a warm type of occluded front. In this case, we have maritime polar air overrunning the continental polar air. You might be like, wait, polar and polar. But as it turns out, the moist air runs faster than the dry air. So it goes up and over. Okay. So another front, now remember I told you there was 4 main fronts. We had the cold front, the warm front, the stationary front, and the occluded front. This is like another front. Actually, there's probably even more fronts than this. But dry line is a type of front between 2 air masses. The air masses are both warm, so we have tropical in both cases, but we have a dry one, continental tropical, and we have a moist one, maritime tropical. Okay, so let's see if we can see that. Well, we can see it simply by looking at this purple continental, oh, that's not it. We can see it by looking at this continental tropical, dry and warm, and this maritime tropical, moist and warm. But even if those weren't drawn in there, we could tell that there was a difference in dry and moist if we looked at their dew point temperatures. So remember way back at the beginning of the class, let's pick on this one up here. We talked about if you have a little station they're called station model icon like that. If it gives you 2 numbers, the top number is the current temp. So this is current, and this is the dew point temperature, DPT. So remember that the lower the dew point temperature, the drier the air. Okay? So if we go down here, we can see we have pretty dry, pretty dry, pretty dry, pretty dry. If we go over on the other side, we have pretty moist, pretty moist, pretty moist, pretty moist. Sometimes this dry line is called a clash of the dew point temperatures. And like this slide says, when we start to talk about severe weather, oh my gosh, are those twisters? Okay. A dry line is a weather front between 2 warm air masses differing in their moisture that can bring severe weather. So there's people who pay to go chase tornadoes. Yeah. Okay. So mid-latitude cyclones. I'm going to spend more time talking about this way that mid-latitude cyclones, they think form and grow and live. Mid-latitude cyclones, that L, crosses the weather map. There's one at the end that I'm going to talk about just briefly. But according to this model, the polar front theory, guess what? It starts with the polar front. So remember what the polar front is, For your unit exam next week, you're going to want to kind of really have kind of a fix on, this is Hadley cell, Farrell cell, this is the polar cell, okay, in both hemispheres. But the polar front is right here. Okay, so according to this model, basically our mid-latitude cyclones kind of start up there, or with that region. But remember, the intertropical convergence zone moves, so that can move too. Okay, so you need to have a central low pressure, and that low pressure will swing air around it in the northern hemisphere counterclockwise. So look for the counterclockwise swing around the low, the cyclonic movement. Now this isn't the beginning. This is not the what they call cyclogenesis. This is in its mature stage. So again, you can kind of see that segment A to B. What does that look like? Well, you'd have cold air, and then a warm sector of air, and then cooler air on the other side of that. Okay. And again, it's kind of setting itself up for what we call occlusion, or forming an occluded front. Why? Because this is going to move fast. One of the things, and you'll see it a few times, let's see, this almost looks like a little, one of those little, well, it looks like a tooth, like where you see the top of the tooth there, and you see the, sometimes though, as it gets started, or gets more mature, it's more just like what we call a comma, like a punctuation mark, a comma. And what I'm circling, that gray, by the way, what I'm circling, that's clouds. Those are clouds. So we kind of see from an aerial view, a comma shape. Okay. So here we see it, the occlusion has started. Okay. We have our central low right here, our L right here, and we have an occluded front kind of sticking out of that, kind of the legs there. And then I mentioned the elongation thing. So here we have that kind of the beginning of the end, or pretty much, I guess I should say it's dissipating at this point. So fully occluded. Of course, the occluded means is referring to the occluded front. So it's, I'm hoping that, you'll kind of, keep your eyes open now and kind of ongoing for those L's that are marching across. Say, do they look like a characteristic mid-latitude cyclone? And what can I expect next? That sort of thing. So all in one fell swoop. Actually, we need to spend a little bit of time talking about how those weather systems march. Of course, I say of course, but they generally grab the surface mid-latitude westerlies, but probably more importantly, what your textbook talks about is those upper geostrophic winds, kind of, even in the jet stream, kind of guide this monster along from left to right. Over North America. So one of the things you want to kind of have a sense of is it starts as a stationary front, okay? Then we get kind of a little wave in it. Then we get a kink in the wave. Okay, that kink in the wave is a little bit of circulation there. And then here we finally have a mature stage. Notice that purple thing. What's that purple thing? Right here. Like, what purple thing? What's that purple line right there? It's the occluded front, yep. And then we have full occlusion, and then we have dissipation. So here they are, A through F. Did I take any words here? No? Okay. Okay, because I was like, I didn't remember taking any words. Okay, so this looks more like something we've been looking at. So you see the L, that's the cyclone. Mid-latitude cyclone, perhaps. One of my things is, well, how do you know if it's just a cyclone or if it's a mid-latitude cyclone? I don't know. Call it what you want to call it. Okay. So we can, of course, those black lines are isobars. And you can see the precipitation from radar information. So the green means light rain, dark green, heavy rain. The red is the heaviest rain. Okay. And again, I mentioned the comma, not to be confused with a coma. So here is the comma. And it's generally, to me, kind of, it's the circle around the central low, and it kind of goes down along the cold front. And of course, we do have some overrunning here. That's supposed to be overrunning. Which that word? Another mid-latitude cyclone. Okay, and again, we've been talking about the air masses that are meeting up. Continental polar, maritime tropical, maritime polar. And we have segment G to F here, and segment E through A here. This is actually, now that I'm looking at it, it talks about, you know, we talked about lows in general bring cloudiness, whereas highs bring clear skies. And why is that? Because we have, at a low, we have converging air and piling up and being lifted up. Okay, so there's a satellite image of a mid-latitude cyclone. So your cold front would be right here. Dry slot behind the cold front. Your head is where your L and your occluded front would be. How many more slides do we have here?
Not a whole lot. Not very many.
Okay. All right. This is good. Okay, so one of the things I want you to get out of even an earlier chapter and this chapter also is this idea of surface highs and surface lows. So hopefully we're all on the same page here. I'm going to put an H under anti-cyclone, and I'm going to put an L under cyclone. Okay? That's something we talked about before. And we know all sorts of things about anti-cyclones. You know, they go clockwise, they're clear skies. The air is leaving the area, and all sorts of things about cyclones. And actually, this is something we're going to revisit. This idea of a, I'll just go on to the next slide. This idea of upper level winds, geostrophic winds, having a little bit of waviness to them. We actually talked in terms of them being Rossby waves the other day, okay? We call that meridional flow versus zonal flow. So we also talked about, I'll put an R here for ridge, I'll put a T here for trough, I'll put a, oh goodness, I think I put an H here for ridge, and I'll put an L here for trough, H for ridge, L for trough, and that's all consistent with what I still want to talk to you a little bit more about. Okay. So we have high anticyclones, low cyclones, and if we do have kind of this meridional or wavy flow, a lot of times you're going to kind of see that nested in, oftentimes, the jet stream. If we kind of think of that flow aloft as being kind of basically the mark of the jet stream, the polar jet that is between the ferrule and the polar cell, that should work pretty good. Actually, it does say polar jet, doesn't it? There you go, polar jet stream. So we talked, and I'm just gonna kind of reinforce a little bit of what we talked about. It must have been in chapter 7 or maybe 6, I don't know. But we said, in order for at a high, this is a high pressure at the Earth's surface down here, okay? A high pressure, basically, you have air leaving the vicinity. Why? Because it's going from a high to a low. Well, if that's the case, then your high is it's gonna quickly diminish. So it actually needs to be replenished, and it is replenished by basically a column of air coming down. Okay, and then that kind of gets to, oh my goodness, if we have a column of air coming down, that air is getting more and more pressure, so it's being squeezed. And what do we know about squeezing air? We know that it is warms. So we have adiabatic warming. So that's kind of what's all going on with your cyclones. And they are associated with ridges, and I'll kind of talk about in a minute how that works with convergence aloft. Your lows are associated with troughs, and the thing about a low at the Earth's surface, we said, oh my gosh, a low at the Earth's surface basically is kind of creating a vacuum, so we have air moving into the area. Well, if we don't do anything with the air, it's going to build up and make a high. It's basically going to convert your cyclone to something else. So that air needs to go somewhere, and it goes vertically. And so that actually is why we see air rising here. And why does it rise? Actually, because we have divergence aloft. And we'll talk about that on the next slide. So we have divergence aloft here, and we have convergence aloft here, that you're going to see on the next, kind of on the next slide. But at the bottom of this slide, at the bottom of this slide, I need to mention, why are we talking about this again? Well, what the jet stream is doing or not doing actually is a steerer of these large weather systems down here. You're like, dude, can't this high move or can't this low move? Well, it kind of depends on what's going on up here. So, again, I kind of just want to revisit that idea of what's happening at upper elevations. We can get divergence or convergence by air speeding up or slowing down upper elevations. If it speeds up, it's basically, if you go vroom, you basically kind of leave a void, you leave a low pressure in your wake. If it slows down, it kind of crunches together, creates a high. We also can have, it's called vorticity, kind of just the way it's kind of kinked up or not kinked up, squished up or not squished up. That also kind of creates divergence and convergence. So you're going to see both of these things on the next slide. But like what we've been talking about now in this whole unit, this idea of we have ridges and troughs, and ridges and troughs. And ridges are associated with highs, and troughs are associated with low pressures. So here we go. So I mentioned, let's see, what was it called? The vorticity that I mentioned. Probably, I don't know if it's also acceleration, deceleration. But the way it works is kind of in this vicinity, downstream of a ridge, right here, a little bit downstream of a ridge, is where you're going to basically have the air kink and create that vertically downward moving air that you need to sustain your low. And then here, kind of coming out of a trough, where the air is in upper elevations is moving right here, that is where you are created kind of a vacuum, divergence, so basically that can allow air to move up vertically. So it's one big giant picture of how these things work. Okay, so we're just gonna, I think, knock this out in one segment if that's okay with you guys. Okay. So it's funny how we kind of, with hurricanes, think about it, we kind of give them personalities. Have you ever kind of thought about, we give them names, okay? And so actually we talk about the birth of a hurricane. Well, that's kind of what your textbook does a little bit, the birth of the tropical cyclone. Where does that happen? So those kind of pink areas are regions where these central low pressures that are important to mid-latitude cyclones can be created. Now, I was looking at this, and I'm kind of like, I told you guys that it kind of starts with the polar front, stationary front, and kind of, so you're like, wait a minute, polar front? I don't think so. But actually, I have one more way to show you how, it's called the conveyor belt method, the conveyor belt theory about these mid-latitude cyclones. So these are where they're born. The other thing you might find interesting is this one right here. So mid-latitude cyclones go by regional names. The Panhandle Hook storms, I may not have heard of, but I know I've heard of Alberta Clippers. An Alberta clipper is a weather pattern, a mid-latitude cyclone that is born here and moves across Canada. Born in Canada, it moves that way. Okay. You've probably heard of nor'easters. Those are mid-latitude cyclones. I probably first learned it as extratropical cyclones, but mid-latitude cyclones that start here and move up. I think probably around a high. I'm thinking clockwise. Okay. So, I think that's interesting. So mid-latitude cyclones, like I said, are kind of driven by what's happening at upper elevations. I mean, they're a I think they're mesoscale. I don't think they're macro scale. Mesoscale, I'll have to double check that size-wise and how long they last. We talked about these isobaric charts, and if you look at an isobaric chart that is 500 millibars, which remember down here we're running about 1,000 millibars, so 500 millibars is about half the pressure up to the edge of our atmosphere. I say, but you know it's not halfway because we've got a lot more stuff down here, so it's probably about down here anyway. So if we get a sense for what the winds are doing there, we can get a sense for where your mid-latitude cyclone is going to go. So this is an alternative to the polar front theory of how mid-latitude cyclones form and move. And it's called the conveyor belt model. In the conveyor belt model, there are three chunks of air that kind of catch a ride on these little conveyor belts, and they go different directions, and ultimately create the same thing we've been talking about, mid-latitude cyclones. We have warm, moist air being lifted up to form our cold front. We have cold, moist air being lifted up in front of the warm front. We have cold, dry air behind the cold front. So it's very busy. This figure is, I think, very busy. But here is, if you start with our warm air being lifted up and over the cold air in front of it, and descending cold air, looks very busy. But we'll have to take their word for it. The conveyor belt model, like what we've been seeing, kind of gives our characteristic mid-latitude cyclone. But like I said, I think it makes more sense for like those source regions that are kind of south. Keep going. Okay. So we're switching gears just a little bit. So when you read this slide, hopefully anti-cyclone, are you thinking H or L? Anti-cyclone. What do you think? Got a 50-50 chance. What anti-cyclones? You're thinking H's. Yep. These would be our H's associated with ridges. Yep. But what this says is actually sometimes your H can move in and won't move out. Okay? It's like relatives. No, I'm just kidding. But one of the things we know about high pressures or anticyclones is they bring dry, warm, dry air. Now, if they don't move along, actually just their presence can, if you have an issue with emissions, just keep those emissions where they are, pollutions. So this is an example of a stalled anticyclone. And it just so happens that this air mass associated with this anticyclone is Arctic. And actually, my notes are kind of old here. If you want to take the Arctic and go put a CA in front of it, that would be great. Because remember, we talked about Arctic is even bitterly cold compared to polar. And there's really only a continental Arctic. There's not really a maritime Arctic because the air's too cold to hold any moisture. But this says we get these Arctic outbreaks several times a year, possibly. Now this is a little bit different. Here we have a high, an anticyclone, a blocking high, but what's significant is basically it's sitting in place so that the low in front of it, associated with the trough, it's not moving either. So blocking high just basically says nobody's going anywhere. Freeze. And if basically you get a cyclone that's got all sorts of moisture associated with it, you can get rain and rain and rain and rain and rain. So this blocking pattern can bring drought to the anticyclone people and can bring flooding to the cyclone people. I think cyclone, cyclops. Cyclone. Okay, and that's actually what happened to a couple of major flooding events for us. So this is another sort of situation where we can get stuck with a low, but it's not a blocking high. It kind of reminds me of, remember we looked at an air mass can be pinched off by kind of meandering flow. We looked at that before, and that's what this kind of reminds me of. Basically, a low has been pinched off. You kind of see the groove. The pink is the groove there. The pink is the jet stream. And it's not connected with the jet stream anymore. It's on its own. So like the slide says, that low can just stay and stay and stay. Not kind of moving on like you would expect it to. Very good. Well, that went faster than I thought it was going to.